So all this time we've been talking about light as being a wave, but at the end of the 1800s and early 1900s, when scientists were looking and studying light and also studying the early atomic theory, remember this was around the discovery of the electron and discovery of the proton. What they noticed is that the wave theory of light doesn't explain several natural phenomena. The first is simply black body radiation. This is emission from hot objects. So if you take your burner on your stove and turn it on and it gets red and glows, that's light being emitted from the hot object, the hot burner pan. But wave theory of light doesn't really explain that well, particularly if we think of light as being an energyless wave. The next phenomenon that isn't well explained is something known as the photoelectric effect. So the photoelectric effect is a case where we have a metal surface, and they noticed that if you shone light onto the metal surface, you'd actually eject electrons from it. And it also ended up being dependent on the wavelength of light as well. And that was really not explained at all by this theory of light as just an energyless wave. And the last one is emission spectra. So if you've ever seen a neon sign, that's the neon gas being excited by an electrical discharge and then emitting light. How does that work from this wave theory of light? So those three really were main considerations that made scientists look a little bit more deeply at the theory of light itself. And there was a scientist in the early 1900s known as Max Planck who looked at this and said, oh, light really is not well described as only a wave. It really should have energy associated with it as small energy packets known as quantum. He was able to relate the energy of those energy packets to the frequency of light in this equation here, E equals h nu, where nu is the frequency and then h is this constant known as Planck's constant since he postulated it. It's 6.626 times 10 to the minus 34 joules seconds. Now, after Planck, and actually at the same time period, another physicist came along that you've probably never heard of. He's not well known at all, Albert Einstein. And he took the equations that we had previously relating wavelength and frequency and rearranged for frequency, and substituting that into Planck's equation above, he was able to come out with an equation that relates the energy of one of these packets to the wavelength of light. Now here you'll notice that he started calling these packets of light photons. And also, you'll notice that this equation treats light as both a particle, a photon, and a wave, because it has a wavelength. So that's where we get this kind of wave-particle duality, which you'll learn more about in physics. The important thing to note here is that there's this direct relationship now between energy and wavelength, and that they're inversely proportional. So a long wavelength means low energy, but a short wavelength would be a higher energy photon of light. Now he used this was just a theory at this point, but he used it to explain one of those phenomena, which is very perplexing to scientists, the photoelectric effect, where it really depended on the wavelength of light, whether you ejected electrons from a metal surface or not. And this theory now explains that, because we can see that shorter wavelengths of light would have higher energy. Higher energy could be used to basically eject electrons from a surface. But lower energy light, longer wavelength, might not have the ability to eject electrons from a surface. And that particular energy where you have enough, that particular wavelength of light or energy where you have enough energy to emit electrons from the surface is known as the threshold energy. Now let's look at a brief video that sort of describes the photoelectric effect in a little bit more detail.
We're in the demo lab with Lonnie, where he set up a photoelectric effect experiment. He has white light impingent on a metal, and the energy of the photoelectrons emitted are shown on the meter at right. If he puts a red filter in the path, now only red photons can strike the metal, and you can see they do not have sufficient energy to eject photoelectrons. If we go to higher energy photons, say go to yellow light, that's shorter wavelength and higher energy photons, they may be able to eject photoelectrons. And indeed, photoelectrons are emitted, but with a relatively small energy. If we go to higher still photon energy, green wavelengths, that's shorter wavelengths still, higher photon energies, we can see photoelectrons emitted at a higher energy. Now we can still go to higher energy photons. Blue photons, photons in the blue region, are the highest energy visible photons, and Lonnie has a blue filter that will pass only blue photons. Putting the blue filter in the path shows photoelectrons emitted at the highest energy. So here's an example of the photoelectric effect. Thanks, Lonnie, for that great demonstration.
So I hope that that's helpful in understanding the photoelectric effect here, where you can see definitely the energy plays a role and is directly related to the wavelength here. And Einstein's equation really explains this. So let's do an example of calculating the energy of a photon of blue light that has a wavelength of 445 nanometers using this equation. So we have the equation energy is equal to Planck's constant times speed divided by the wavelength. And we could just plug these values in, but we'll note that our wavelength is in nanometers, whereas our speed is in meters per second. So the length unit will not cancel. So the first thing we have to do is convert nanometers to meters so that it will cancel with the meters in the equation. So take 445 nanometers, use the conversion factor between nanometers and meters to convert to 4.45 times 10 to the minus 7th meters. Now all of my units are appropriate, and I can plug them into the equation to solve for the energy. And what I come out with, if I multiply through, is 4.46 times 10 to the minus 19 joules. It's a very small energy. That's 18 zeros in front of the 4 after the decimal point. So this is an extraordinarily small energy value. And it might be more convenient for us to have a unit that doesn't contain such a large exponent when we're talking about energy. It's something that's a little bit more appropriate for the energies of light. And we actually have a unit for that. It's known as the electron volt. 1 electron volt is defined as 1.602 times 10 to the minus 19 joules. And so now if we revisit that problem that we just did and look at the energy of a 445 nanometer blue photon, we can see if we take the energy we'd calculated, we can convert that to a much more manageable unit, 2.78 electron volts. Now I have no ginormous exponents, and I can deal with things simply on this one kind of order of magnitude here. And electron volts are really useful when we talk about energy specifically for visible or ultraviolet light. We do have to convert back to joules whenever we are using the equations to relate to wavelength or to frequency. But it is a useful tool when we're talking about the energies of light. We can look at the whole spectrum and see that right around the visible region in the ultraviolet, that's where we're talking about electron volts or energies on a scale of 1 to maybe 10 electron volts if we get deep into the ultraviolet. But then what we'll see is that as you get to smaller and smaller wavelengths, such as X-rays or gamma rays, the energy goes way up. So remember, energy and wavelength are inversely proportional. So as the wavelength goes down, the energy goes up, and then vice versa. As we get to longer wavelengths, we get to very low energies. So if we're out in the radio region where it's 10 to the minus 10 electron volts, you can imagine for joules, that would be like 10 to the minus 29 joules. So an extraordinarily small amount of energy for those light waves.